Alright, so we're going to take a look at a couple different example questions using our table that's here, and we'll kind of start off with each one. I'd encourage you as we go through each one, pause the video for each part, each question, and try them out using the table and see how you make out with it, and then come back when you're ready to go over the answers for each one. So in our first example, what is the pH of a solution with a hydrogen ion concentration of 4.2 times 10 to the negative 10. So again, pause the video, take a look at the table from the notes, and see if you can make that work within the equation. Alright, so hopefully you had a chance to take a try at it. It does give us the hydrogen ion concentration here, so it does say that our H plus is equal to 4.2 times 10 to the negative 10 for a molarity, and it wants us to get from H plus to pH. Okay, it's saying what is the pH of this thing. So if I want to go from H plus to pH, then I can see that I'm going to need my negative log equation to get there. So I have pH is equal to the negative log of H plus. pH in this case is the negative log of 4.2 times 10 to the negative 10. And my pH value, when I plug in those numbers, again, you can do log of 4.2 and log of 10 to the negative 10, or you could just punch it in all in one step on your calculator. You do get 9.3767, and that would be our pH value. But the question is kind of where do you stop? We've talked a lot about significant digits in the past, so where would we kind of stop with our rounding part of how many digits do we keep? So the answer to this question is actually a little bit different than likely anything that you've been taught so far for rules, and it's specific to logs. So how you calculate it is based on the number of digits in the ion concentration. So in our ion concentration, 4.2 times 10 to the negative 10, there are 2 significant digits. However many significant digits there are, that's how many decimal places the pH value will have. Okay, so basically the rule is however many significant digits there are in the ion concentrations that's how many decimal places. In the pH system. Okay, so however many significant digits there would be in the ion concentration, that's how many decimal places we're going to have. So really my final answer here, with the right amount of significant digits placed in with it, is 9.38. Okay, that's our pH. That one is new, and it'll take you a second just to kind of wrap your head around it, but you will have a chance obviously to practice a bit too. So the next example, the pH of an unknown solution is 6.35. What's the hydrogen ion concentration for that? So again, pause the video, go back to the chart, take a look, see if you can figure it out, and come back when you're ready to go over the answer for it. Alright, so let's give it a try. Hydrogen ion concentration is what we're looking for. It gives us the pH value, and so it tells us that the pH is 6.35, and we're looking for the H plus in this case, and so if I were to look at my chart, I would see that in order to get there, now I have to go essentially backwards from what I had from before. So now I'm given pH, and I need to get to H plus, so I can see that I'm going this way, right, from pH to H plus. So H plus in this case is 10 to the minus pH. Now notice that it's not 10 subtract pH, it's 10 to the exponent of negative pH. So in this case, H plus is equal to 10, and then the exponent is negative 6.35. H plus is equal to 4.47 times 10 to the negative 7 for molarity. And then remember that however many decimal places we had told us how many significant digits there were in our ion concentration. So there are 2 decimal places in our pH scale. So our H plus is going to have 2 digits for an answer. 4.5 times 10 to the negative 7 for molarity. So we do have one other example to go through. What's the pH of a solution if OH is equal to 4.0 times 10 to the negative 11? Again, encourage you to pause the video, see if you can figure it out, and come back when you're ready. All right, so in this case, we're given the hydroxide ion concentration, and we need to get to pH. So let's go back to our chart. So we're given the hydroxide ion concentration, okay, we're given this, and we need to get to here, we need to get to pH. So hopefully what you can see here is actually 2 separate ways we can do this. We can go this way to get there, or I can go this way to get there. And both of them should give us the right answer. So whichever way hopefully you pick to give this a try, hopefully you're able to arrive at the correct solution for it. So let's go through, I'm going to do each one so you can kind of see both ways and how they would work out, and how both should be able to give us the correct answer. So the first way, I'm going to go up and then to the left from our chart. So if we had a pOH value, the first step we'd have to get into, the equation tells us that we have to use the negative log of our hydroxide ion concentration. So then pOH would equal the negative log of 4.0 times 10 to the negative 11. And then our pOH value equals 10.39794. And because there's only 2 digits in our ion concentration, I know I'm going to have 2 here, but I'm going to keep all my values so I don't make any rounding errors. After that, I'm going to go through and do my next step, because now I'm in pOH, and I have to get to pH. So pH is just 14 minus pOH. So pH is equal to 14 minus 10.39794. pH is equal to 3.60. Keeping in mind here I had 2 digits from the first one, I've got 2 here. That 14 is a constant value. It could have infinitely many zeros after it because 14 is the set number for pH plus pOH. So really I'm just taking my digits from my given term in the question, or pOH. So I get 3.60 as an answer. But what if we tried it the other way? So both should work out here. If I try this the other way and I go left first and then up, I've got my formula to find the hydrogen ion concentration, and that's Kw over top of my hydroxide ion concentration. Hydrogen ion concentration, we know that this is 1.0 times 10 to the negative 14. And my hydroxide ion concentration is 4.0 times 10 to the negative 11. And so when I divide this out, I am going to put this in scientific notation. It will probably give you a full number in decimal form. And so that's okay. It's just normally when the hydroxide ions are written out, or your ion concentrations are written out, they're in scientific notation. So for this one, I get 2.5 times 10 to the negative 4 for a molarity. Okay, and again, you just take the decimal, move 4 places to the left, and you'd have it worked out in expanded form. So that's my first part. Then after that, I have hydroxide ion concentration, and now I have to go to the pH value. pH value is the negative log of my hydroxide, my hydrogen ion concentration. So it's the negative log, and I'm plugging in that 2.5 times 10 to the negative 4 for a value, and I'm finding that the pH, when I punch in my numbers, gives me 3.60, which is really good because that's exactly what I'm looking for, hoping I'm going to get there. So it doesn't matter which way you go, you end up getting the correct answer. So, acid-base indicators, they're really valuable tools for measuring pH because they have different colors in their solutions, and there's all kinds of different chemicals that can be indicators that can tell you if something's an acid or a base. So there's a chart on page 602, and I want you to just kind of briefly answer the interpreting graphs section that's just off to the side of it. So I'll get you to flip open your book, take a look at page 602, and just answer some of the questions that are there for the interpreting graphs part, and come back when you're ready. All right, so the A part for the interpreting graphs is, I'm just going to run through the answers just really quick for you for them. The A part is, hopefully you had thymol blue. The B part, in terms of indicators, the indicators change color over a really small range of pH, and so the indicators change color over a small range of pH. And in C, we've got two different types that could be your right answer here. It's only looking for one, but you're just looking between pH of 3 and 5. So it's that bromophenol blue. Could be one indicator, even though it doesn't necessarily go all the way, but it goes pretty close. Or you could have also said the bromocresol blue, bromocresol green also would do the trick. And that one is actually probably more closer in between your 3 and your 5, but both would work. So hopefully it just gives you a chance to take a look at a few different parts of calculations over the last couple of videos, as well as just kind of how indicators work in general and that kind of stuff. So I do have a couple of questions for you to go through out of the textbook, as well as there's some log questions to work on that are on R79, and R79 is actually in the back of the book. So if you were to flip toward the end, you'd start to see a bunch of pages with R's. It's some log questions to go through, just to practice logs, numbers 1 through 4. So that's everything for that section, and let me know if you have any questions.